I want to take you on a journey of what we call a request, and specifically an HTTP request, because that's the most ubiquitous and abundant type of request that is in the web, obviously, right? Keep in mind that the anatomy of a request that a front end makes to a back end doesn't have to be an HTTP request. You can do like what the game developers do, and they go deep down into the networking stack and pick a protocol that is so low level, and they build their own protocol because they don't need all the crap that HTTP has. You know, they send a single byte, and boy, they cram as much information in that byte as possible, right? A byte is 8 bits, and then, boy, they can send 8 commands. They can send 8 different commands in a single byte, you know. Doesn't have to be a text, right? It's just this always fascinates me, how much wastage are there in HTTP, but it is what we have, obviously, and it's being compressed and being compact as much as possible. But regardless, it's not our topic. Our topic is let's follow the journey of a request. Exactly what happens when you take that request and delivers it to the backend, especially when the backend is really not the final destination. There is another backend behind the backend, you know, because usually in an enterprise level architecture, and when you have like an actual, you know, production level system, you have all these layers that your request has to go through. Most of these are an API gateway, which is nothing but a glorified reverse proxy, by the way, right? And behind that could be a load balancer, you know, which is, again, nothing but a glorified reverse proxy. But at the end of the day, what really happens, and what's the kind of latencies that the request faces before it reaches, you know, the final, you know, destination, which is actual web server that understands how to respond to that request. Let's go into this journey. Welcome to the Backend Engineering Show with your host, Hussein Nasser, and let's follow this journey of the request, an HTTP request to be specific, right? So let's say you have a link and you receive this link via WhatsApp, or maybe you actually have that link in a page that you have already loaded. So there is already a domain that is being loaded, and this link is one of them. You try to click on this link, or you actually typing that link in the browser and hitting enter. The three scenarios yield completely different results, but I don't have time of it to explain all these scenarios. So let's take the WhatsApp example, or the messages. You received a link from a message and you clicked on that link on your mobile phone. What happened is the operating system will detect that, oh, this link is an HTTP link, so we need a browser to understand how to, render this link, let's say. First of all, we open a browser instance. So we detect what is your default browser. So we open that. If we don't have a default browser, we prompt you. And by we, I mean the phone here. And then we open a browser, regardless, Chrome, Safari, you know, Opera, whatever is the default browser. And then we open the browser. Now we deliver the link to the browser. And we say, oh, this is an HTTP or HTTPS link. And here is really what is really critical. Was the link sent to you starts with an HTTPS : / or HTTP : / and really makes a difference. So let's say we start with HTTPS. Okay? If we start with HTTPS, then the browser knows that the domain that I need to connect to lives on port 443, because that's the default port usually. But before even we do that, we really need, in order to connect to, we need the port, which we know now because it's HTTPS, and we need the IP address, which we don't have. We have a domain, right? Because let's say this domain is facebook.com/, let's say someone sent you a Facebook post, right? You wanted to view that. And facebook.com. So the browser says, okay, what is the IP address of facebook.com? We do what we call the domain name query to get the IP address. Say DNS. So we deliver this query to the operating system to figure it out, right? And we depends on the configuration at that end, what kind of DNS is configured. You know, do we have a pure vanilla DNS, which is on top of UDP, or do we have this fancy new thing, which is DOT or DOH or DNS security? And then we resolve the DNS using the appropriate approach, right? It's an episode by itself, DNS resolution. So now we find my domain name server that is configured on the phone, which is retrieved from my router, which is probably configured by your admin, or maybe you have overridden that on your phone, and we use that DNS server, whether this is Google 888 Air, Cloudflare 1111, or any other domain provider. Or maybe you have your own DNS provider, you know, like a Pi-hole or whatever. So now we ask that question. And the facebook.com, we go to a root server, which then takes us to, you know, one of the 13 root servers. And then the question is like, okay, where is .com, right? Because we want facebook.com, but we have to answer the .com servers. So we go to the top level domains .com. Give me a .com server. There are millions of those. So we go to one of them and we ask, okay, give me, tell me where facebook.com is. And facebook.com is like, this is where you can get the answer of facebook.com. So you get another server, which is called an authoritative name server. We go to that, and then that gives us the answer to our facebook.com. So authoritative name servers usually belong to Facebook, right? So this is all done by the DNS recursor on the background, probably synchronously, while we are blocked waiting, right? Assuming we don't have any cache, obviously. Until we get a result. We have a beautiful IP address. This IP address is usually the IP address of the first front-end reverse proxy that all the request goes to, right? And now we have a beautiful IP address in the client side. And now we also have a port. Now we can establish a connection. And for simplicity, I'm going to use HTTP2. HTTP3 is a little bit different. We use the quick, and I don't want to get into the complexity of quick now. Most of the web now is on top of HTTP2. Although Facebook now uses HTTP3 and quick almost exclusively. But for the sake of example, let's simplify the story. Okay. So now we establish a TCP connection, right? With this IP address that we just got on port 443, because that's what we need, right? We need this pair. And obviously, to establish a TCP connection, we have an IP address, and we have also a source port that is almost random, that is used for facebook.com to know how to respond to us, right? Because a TCP connection is always, we need these 4 pairs. This is very critical to understand these 4 pairs. The 4 pairs is destination IP address, where you're going, destination port, which application you're going to that on that machine, right? On that host, right? And the source IP address, who are you as a host, and which application is actually running, right? And that's basically the unique configuration. We basically establish a TCP connection through a 3-way handshake, sync a SYN-ACK and an ACK, and then now we have a stateful, beautiful TCP connection. we established sequence numbers so that we can label our segments, right? It's like, hey, this is segment number 1. Obviously, it never starts from 1. It starts from a very big, large numbers that both the server and the client agrees on. And now we have some sort of a state going on. TCP is stateful. We know that. That's not enough. We have a TCP connection, beautiful. But the next thing is, because we know it's the HTTPS, we have knowledge, knowledge of this beautiful link. We need to establish on top of that unencrypted TCP connection, plain text. We really need to establish a TLS. We talked about TLS many times. And the reason is we really need to establish session keys, ephemeral session keys that is only used for this particular connection. So we use Diffie-Hellman to exchange this session key. So even if someone in the middle trying to really intercept and understand what's going on, they can't, right? And we send the client hello, TLS client hello. The server responds back with a server hello with a certificate proving that you are in fact talking to Facebook.com. In the TCP side, there is no authentication. We don't know that the IP address that we got actually belongs to Facebook. We have no knowledge about that. The TLS helps us authenticate and encrypt, right? Authenticate, that means, hey, are you who you say you are? Okay? And it is done by this thing that is called certificates, right? So Facebook will reply with an actual digital certificate that has the string facebook.com in it, and is signed by some trusted party called the certificate authority, which is signed by another trusted party called the root certificate that everybody's trust on their machines, unless you're a Chinese laptop. Okay, so now we have this beautiful hierarchy of this. We have trust. I know that we're talking to Facebook. We established an ephemeral key that we use to encrypt using symmetric encryption because it's faster than asymmetric public key encryption, right? And then now we start encrypting. Now the application is ready to actually start sending the request. So a click that we have done on the WhatsApp translates to a GET request. That's a GET request, always a GET request. So we need to send an HTTP GET request, right? And obviously we have agreed on which protocol we are using with Facebook in the TLS handshake, right? This is done by using something called ALPN, application layer protocol gateway. And now we know which application we're using, right? We're using which protocol we're using. Is HTTP 2 or HTTP 1 or HTTP 3. And now we know we're using HTTP 2. So let's go ahead and send our first GET request. We need to construct this GET request. What are we sending exactly? Where are we going? We're sending the GET request. That's the method. HTTP needs also the protocol, so HTTP 2. All right. The third parameter is actually not parameter. The third bit that we need is the path, and the path is clearly in the link, right? Because facebook.com/ blah, 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 that's the whole path. And sometimes there is like funky wonky query parameters which starts with a question mark and blah 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 and it's percent blah blah blah. So that also is added on top of the path. So we have this GET request, we have the path, and now before we send this, wait a minute, all right, we need to send this, and this is the domain. What kind of headers do we need? Well, the host header, this is a very required header, host header. Where are we going? We're going to facebook.com, blah, facebook.com. Put it there. You might say, why are we putting redundant information? We know that we're connecting to facebook.com. No, actually, we lost that knowledge. We did it in the DNS, right? And then we got it from the TLS, which is as a certificate. But then we lost that knowledge. We lost it. Right? So we need to, HTTP is stateless. It doesn't know this stuff. So we need to carry on that we're actually, hey, I'm actually going to facebook.com. You put it as a header. Optionally, we need to also authenticate this request that, hey, by the way, I have visited facebook.com before. I have logged in on facebook.com before, and the browser remembers that and says, okay, where are you coming from? You're coming from WhatsApp. All right. This is a click link. So it's as if you went to the browser and actually typed Facebook.com and you hit enter. Most browsers treat that as equal. Some don't. Wow. Okay. Some don't. But now we have a beautiful, authentication that we can send. It's called cookies. So the browser now makes the decision, should I include the facebook.com cookie because it's already there? I saved it locally. If I include it, then Facebook eventually will get that. So we include, let's say we included cookies. Boom, put the login information. And now we package this beautiful GET request. There is no body in GET request usually. I say usually because I never seen one, and I think that's the standard really. But some people say that can be broken. Everything can be broken at the end of the day. And now you take that beautiful payload, and that could be large payload, right? Now we need to send it on the TCP vehicle. That's the vehicle we have. Well, what do we send in TCP? Well, we send segments, right, which translate to IP packets. But the TCP segments here, let's say, for the sake of example, that beautiful request that we have, the GET request, which has a long strings of stuff, right? Maybe we compressed it, right? And we did header compression with HPAC with HTTP2. We did so much stuff. And that beautiful string of bytes, we need to send it. Now, it depends on the maximum segment size and the window size that we have been agreed upon on the TCP, stack. We can only send this much. This is called the TCP slow start. You start slow, and then if the TCP stack sense that the backend actually can handle more, it will increase the segment size and you can send more and more data. So let's say I can only send X amount of segments, right? And my request is too big, so I have to break it into 4 segments, right? As a start. Now, 4 segments. And here's where the algorithms kicks in. Should you, as a client, the client being the mobile phone that had the link from WhatsApp and all that jazz, right? Should you send the first segment, which is probably going to be nonsense, right? In the grand scheme of thing, because it's going to be chopped up GET request. It's not going to be the whole thing. Should you send that segment and then wait for an acknowledgement of the server that you have actually received that segment? Or should you send the 4? Most clients will behave and says, no way, no really. We really need to send 1 and then wait, because there could be a congestion going in the network and I have no idea about the state of the network. So I have to test the network. I have to, I have to play with this network. Okay, take this few bytes. Can you handle this? Can you handle this? And then we send it and we wait. If we receive an acknowledgement, that means, hey, this seems like this server actually can handle this. But we took a hit here because we sent a single segment that is part of a GET request. Remember, this is not the full request yet. We sent just part of it. The client is now waiting. You're waiting for facebook.com to open. But we never actually delivered the request yet to the backend. I want you to really pay attention to this, because this is very critical, especially in the backend when you work with Nginx and load balancers and HA proxies and stuff like that. This is the low level stuff that you play with and you have to understand. So now we sent a segment. There's part 1 out of 4 of that HTTP request that I'm about to send, right? The backend now here, let's say this is the API gateway. That is the front end of Facebook talking to us. Right? That's why I always say, like, every backend has a front end and every front end has a backend at the end of the day, right? A backend is always a front end of something else. So now we receive that segment in the backend, and we send back an acknowledgement. Okay, I got it. But now we took a hit of latency. Whatever the round trip time, let's say X millisecond, we took it. Like, minimum is like latencies when these comes thing is like 20 millisecond, 40 millisecond. You're gonna get lucky if you are like going to Google and you have like a server next to you. You get maybe 5, 8 milliseconds. I never seen less. You only get like sub millisecond when you're on local network. But you almost never get 10, 5, 6 millisecond if you're going to the internet, right? You're taking the hit. So 4 milliseconds going or 10 milliseconds going or 40 milliseconds going, 40 milliseconds coming back. So there is a 80 milliseconds hit, right? And now you send the second segment. And let's say the client decided that it's too slow. So let's be patient and send the second segment and wait for an acknowledgement before we send the third segment. So now we take a 40 milliseconds. So we take another 80. So the 160 millisecond, you might not feel it. 160 millisecond is not sub-second. But do that again. 160 plus another 80. Do the math. 220? 220. Yeah? 220 milliseconds. The fourth millisecond, now 300 millisecond is what users usually feel. It's just, you start feeling it. So you took 300 millisecond, 300 something, right? Millisecond, even more than that, just to deliver the request to who? Not your backend. That's just to deliver the request to the API gateway, which is the front-facing reverse proxy. We didn't even reach the backend yet. So now the backend, which is in this case the API gateway, says, okay, I got 40 requests. Okay, this makes sense. Now these 4 segments combined, oh, now I understand what this is. These are actually part of one stream, right? Because that's how HTTP2 works. And now this beautiful string of bytes compose a beautiful GET request with the cookies and stuff. Now, obviously, there is decryption on top of that I didn't talk about. We use the symmetric key that we agreed upon with the API gateway to decrypt. And then look at that beautiful stuff. And then all of this thing, now we have a GET request. Now, does the API gateway answer? Absolutely not. The API gateway will say, wait a minute, let's see if you're actually authorized to make this request to begin with. So we'll check your IP address. We'll check the nature of the request. It's a layer 7 reverse proxy, so it sees the request. It's decrypting and it sees your entire request. It might need to do some API rate limiting at you. It does all sorts of checks, and this takes a finite amount of time in the API gateway while you're still waiting. That's a click on WhatsApp. That was one single click. All this time you're doing that stuff. API gateway got a request. Says, okay, you may proceed. And when I say you may proceed, that means I, as an API gateway, now I am a front end, and my actual back end, let's make it simple. Let's say this is the final destination, because I can go on and make it another load balancer, which then another hop, which goes to another backend. But let's simplify. Let's say the backend is actually the final destination, and this is your Apache web server. This is your Caddy. This is your Lint. This is your what kind of web servers do we have? Right? Mongrel 2. This is whatever web server you're using at the end of the day. Right, your IIS, and now you're talking to that. But how? How are you talking to the backend now? The channel between the API gateway and reverse proxy now needs to go through some sort of a similar pattern, right? Either open a connection to the backend eagerly when a request comes, says, okay, you now need to go to this particular server. I'm going to pick one for you, because the client doesn't know anything about the actual final backend. That's what the definition of a reverse proxy is, right? You as a client talks to the reverse proxy, but you don't know the true final destination. It just hides it from you. It's like exact reverse of a proxy. Proxy, you know where you're going and you want some help to take you there, right? That's the proxy. So now you talk to the reverse proxy of Facebook talks to an actual backend. And now this is where the creativity of engineering and backend engineering comes into the picture. What do? Do you establish a connection on that spot, right? Taking the head of DNS, which is not much, but taking the head of TCP connection and taking the head of TLS encryption, 3 hits, then package that request again, send it? Or do you preheat this connection prior in anticipation that someone might actually send a request? There is pros and cons for both approaches, the lazy approach or the eager approach. There is pros and cons, right? Because if you preheat them, you're wasting memory that nobody might use, as now you have something ready that you just ship something to, right? The other approach is hey, let's open on demand, but it's going to be slow, right? The request, you're taking that synchronous request gets the hit of the establishment of the backend connection. Does that make sense? It's all decisions that you can make. There's no true right or wrong. There is nothing like that. It's all decisions that you make based on your workload. So now the API gateway packages that GET request, maybe most of the time adds even more headers to that request and then ships us to the backend, right? And usually the API gateway to the backend, this is a local network, right? Because it's the backend network interface, the neck of the API gateway is different than the neck that talked to the front end, right? It's usually have 2 network cards, like not physical network card, could be virtual, who cares? And then now the backend is almost local, so there's no latency. There's like sub-millisecond, microsecond latencies, right? So now if I send that request, right, I can send it as a whole. Probably there is that's another advantage of preheating, because preheating you can send garbage data to trigger slow start so that we know that we are in a high bandwidth area and we can send that request in one TCP segment. Beautiful, right? Avoiding that whole latency stuff, right? And then you receive the request from the backend. No, you don't receive the request. You receive the request on the backend. Now the backend decrypts the request, takes a look at it, and then decides to actually execute that request. Now this is your Express server, this is your Node.js fancy stuff, your Django, your Python, whatever logic you have. Now you actually execute it there, right? This is maybe a query to the database, you're doing all that stuff. So the response time that usually backend engineers measures is that. Like how long it takes for me to, once I receive that request, right, after it gets assembled to me, your slash get method will be called, the callback, right? That callback will be called with a request only when that TCP segments are assembled into what the backend actually understands as a GET request or a POST request, right? Now you go and do your own stuff, and this is, you try to minimize the response time as much as possible. You do your own thing, and now you compile a response HTTP and do the same thing exactly. You write that response, right, to your API gateway. You don't know. You just write it to whomever sent it to you, right? Whoever established the TCP connection with you. And now, hopefully you can write all the response. If your response is tiny, you can do it in a single TCP segment. If it's big, then it's going to be broken up into the different TCP segments based on the maximum segment size at that point, or the window size at that point. That's the accurate terminology. And then we send it to the API gateway. The API gateway does the same exact thing, decrypts it, because it's a layer 7 thing, right? Both of these endpoints actually needs to go all up to the first stack, which is the layer 7, or the last stack, depends on how you look at it, and then understand that stuff, and then unpack that, and then maybe add some more headers, right? And then now we are ready. The API gateway receives that response, it takes it and then writes it back to the client, which is our phone, right? And now the same thing, we are at the mercy of the internet, we are at the mercy of the TCP window size. How much can I send? And the larger the response size, the more TCP segments you need to send, and the more you have to wait for an acknowledgement for these TCP segments. So now you can play all sorts of games here. Even if you have multiple TCP segments, the TCP stack can send a lot of segments without waiting for an acknowledgement, and you want to be in that state where you can send as much TCP segments as possible without actually waiting for acknowledgement from the server. Because if you wait for an acknowledgement, that means you have a slow connection. That means you don't trust the backend to respond to you in time. That means there is a possibility of latency because now you're waiting, right? So the best configuration that you can get on is when the window size is so large that you can send a gigabyte. I don't know if that's that big, to be honest, but you can send a huge amount of data without acknowledgement. So hey, shove that on the bandwidth, because my bandwidth, the routers in the middle actually are not yelling at me. They take my data, they can send it, and then you receive the response on your client side. And now it's probably going to be an HTML page or a JSON or whatever. Now when we receive that on the client side, we decrypt it with the session key that we use in TLS, right? We decrypt every we decrypt every TCP segments, right? However there is. That's why the encryption algorithm used in TLS must be really fast, right? Otherwise, if it's so slow, imagine doing that with a large number of bits. That's why AES, the symmetric encryption, are usually small, with 128 bits, 256 if you want more security, right? You have to use some number of bits. If you use a large number of bits, then it's going to be slower. That being said, it's going to be very secure at the end. But no one proved that you don't need more than 256 of AES bits in security, to be honest, to receive great security with symmetric encryption. Now, you decrypt segment by segment. You have this beautiful plain text. You combine it, and you now understand it's actually an HTTP response. You look at the headers, you look at the response header, you look at the status code. Oh, is it 200? Is it 4 errors? Whatever. Right? And then you parse the response. Content type, what did we receive? We received an HTML page. We received a JSON. We received JavaScript. We received CSS. And then you do what the browser can do effectively based on the content type. If it's HTML, we render it. If it's an image, we render it. If it's a CSS, we view it. If it's a JavaScript, we execute it. Dangerous sometimes, right? And that's it. That's what we do basically, right? That's the cycle. And that was a single request, guys. Now imagine all the stuff you do. Next time you're gonna send a GET request or a loop of GET request, or you will gonna appreciate the cost of all of that. Right? And that was the purpose of this podcast effectively. Just appreciate what is going on the back end, right? On the networking stack, on the security stack, on the API gateway, on the load balancers, right? And I had only one layer, which is the API gateway. I could have another layer, load balancer. That's another read and buffer, and then rewrite to another socket on the network interface. The operating system latencies. I'm pretty sure I missed so much other stuff as well that I basically don't have knowledge about yet. But I hope you guys enjoyed this podcast. If you want a quick plug, if you like this kind of podcast, consider checking out my first of all, consider checking out our membership here on YouTube. If you join the membership, I have over 60 videos of member-only exclusive content that you can't get public on YouTube, right? So you get access to that. And consider also checking my fundamentals of Nginx, our introduction to Nginx Udemy course, where I talked about these kind of, in detail, the fundamentals of reverse proxies, load balancers, the different configuration that you can put Nginx on, the different ciphers that you can put Nginx on, and do all this kind of cool stuff, right? Talking about the basics, fundamentals that you can apply on your daily job. Consider that. Go to nginx.husseinnasser.com for a discount coupon. Thank you so much, guys, for listening or watching. If you're listening to this on the podcast or Spotify or Apple Podcasts, I appreciate you. Thank you so much. I'm going to see you in the next one. You guys stay awesome.